There are strong acids and weak acids, and also strong bases and weak bases. And here the term strong is used in the same way that strong was used for electrolytes. A strong electrolyte solution conducts electricity well. A weak electrolyte conducts it very weakly. It would make the light bulb glow, but just a little bit. A strong acid is one that ionizes completely. So HCl and HF appear to be pretty similar. Chlorine and fluorine are sisters on the periodic table. They're in the same column, but they're different as acids because HCl ionizes completely and HF ionizes only a little bit. So here's a strong acid, HCl. We put it into solution. The hydrogen ions are donated to the water, and we get hydronium ions plus chloride ions, and there's no individual HCl molecules left. They all ionized. So this arrow is just a single arrow. I haven't made a deal of it, but we saw a few before that had an arrow in both directions. This one's just going in the one direction. It means complete ionization. And so what we'll say about this is a 1 molar HCl solution will have H3O plus equal to 1 molar. And when we put the brackets around a compound, it means concentration of in moles per liter. So this is the concentration of H3O plus is 1.0 moles per liter because it's the same as the HCl, all of it ionized. So if I had 1 mole of this, I'm going to end up with 1 mole of hydronium ions. So pure water does not conduct electricity, but if we put hydrochloric acid in, it does conduct electricity and the light bulb glows. We get a strong light from a strong electrolyte. These are the 6 strong acids. How do you know that they're strong acids? You just remember them. There's 6 of them. Hydrochloric, hydrobromic, hydroiodic. Those are the 3 of the 4 halogen acids. The HF is the exception, but she's the smaller one. It's often the smaller one that's an exception. Then we've got nitric, perchloric, and sulfuric acid, and these are also considered strong acids. Most of these are monoprotic, meaning they only contain 1 ionizable proton. So all of these have 1 H on them, except for H2SO4. This is a diprotic acid. It's got 2 protons that can ionize. Weak acids are everything else. So there's 6 strong, and everything else is weak. Weak acids only ionize a little bit. So you put HF in solution, and some hydronium ions and fluoride ions will form, but mostly what we see is intact HF molecules. So it only ionizes a little bit. These are weak acids. They are also weak electrolytes, and they are poor conductors of electricity. In this equation, we put a double-headed arrow, meaning that it does not go all the way to the right. It's somewhere in between. So here's an example of what happens when you put a weak acid in the solution. The light bulb will glow, but only a little bit. It's a weak acid, a weak electrolyte. You get a weak light bulb glowing, weak light, okay? Because there's only a few ions to conduct the electricity. Here are some of the weak acids. There's lots more. Anything that's not one of the 6 strong acids is a weak acid. We've got 2 diprotic acids here, carbonic acid and sulfurous acid. Phosphoric acid is a triprotic acid. So looking at these beakers, which is a weak acid? What are you looking for? A weak acid only ionizes a little bit, so you'll see molecules, not just ions. So here we've got hydronium ions and iodide ions. Here we have nitrate ions and hydronium ions. There's only two kinds of ions, hydronium and an anion. Over here we have hydronium ions and CHO2 minus ions, and we also have HCHO2. Is this a weak acid? Yeah, because it didn't all ionize. It only ionized a little bit. These are labeled here because it's a little tricky to see which of these is really that different. But this is the weak acid. If a WACID, maybe we should talk about wabbits. If a weak acid, weak and strong does not tell us how dangerous or how corrosive an acid is. That will depend on how concentrated the solution is. Weak and strong refers to how much do they ionize when they go into solution. Okay. So let's look at this problem. Determine the hydronium ion concentration for each solution. So the first thing you have to do in a problem like this is to identify whether this is a weak acid or a strong acid. HCHO2. Well, we probably don't have those strong acids memorized, but they are HCl and HBr and HI, all of fluorine's sisters. And then there's nitric and perchloric and sulfuric. And I really don't expect you to remember those. So is this a strong acid? Is it on the list? No, it's not a strong acid. It's a weak acid. So this is going to only partially ionize. We actually don't have enough information to calculate specifically what the concentration is. We can just say relative to 0.5. So when this dissolves, HCHO2 plus H2O, it's going to be a weak acid. We're going to get hydronium ions, and we're going to get the CHO2 minus ions. But it's not all going to become hydronium ions. If it all became hydronium ions, then the hydronium ion concentration would be 0.5. But it's less than that. So all you can say here is that it's less than 0.5. I find that very not satisfying as an answer. Any questions about that? In Chem 1B, if you take that, you'll learn way more than you want to know about exactly how much. It's a little complicated. So it's just less because it's a weak acid. Let's look at the next one. 1.25 molar HI. Hi. It's a very friendly acid. Is it a strong acid? Yeah, it's on the list. Strong acids ionize completely. So this one is going to ionize completely. Single-headed arrow is going to form hydronium ions and iodide ions. For every 1 mole of HI, you're going to get 1 mole of hydronium ions. So the hydronium ion concentration will be what? It'll be 1.25 molar. It's the same. Because all of those hydrogen ions come off and ionize. It ionizes completely. So for a strong acid, the hydronium ion concentration, for the most part, for a monoprotic acid, will be the same as the acid concentration. How about HF? Less. It's less than 0.75. Why? It's a weak acid. It's not on the list. It didn't make the list. It's a weak acid. So it's going to ionize partially. The hydronium ion concentration will be less than the concentration of the acid. Any questions? Never greater, no. This here, the concentration of hydronium cannot be greater than that, because where would the other hydronium ions come from? Strong bases, the word strong is used in the same way. Strong bases ionize completely. They dissociate completely. If you have a base that has two hydroxide ions, like SROH2, it will separate into ions and give you 2 moles of hydroxide for every mole of the original base. I kind of skimmed over the idea of diprotic and monoprotic acids. They do lose their hydrogens one at a time. We're just going to kind of ignore that. So you put sodium hydroxide into water, it's soluble, it completely forms ions. There's no molecules because it's not a molecular compound. So any soluble metal hydroxide is going to be a strong base. A weak base only makes ions a little bit. The only one that we need to know about is ammonia. So here's the generic equation. The base, the weak base, reacts with water to form BH+. The base accepts the proton. It's the babysitter. So it's taking the H+, holding it for the water, and then we've got hydroxide ion left. Double-headed arrow, it only goes a little bit to the right. So for ammonia, NH3 reacting with water, it accepts the hydrogen ion becoming ammonium ion, and then we're left with hydroxide ion. But it's not a strong base. There is plenty of NH3 still present in the solution. This is an illustration of what happens. So we have intact ammonia, and we've got some ions, but mostly not. There's lots of weak bases. Organic amines are weak bases. The only one you need to know about, though, is ammonia. So determining hydroxide ion concentrations. This is the day of making up new words. Similar idea. Strong bases, they all go to ions. Weak bases, they don't. But here you're going to have to watch out a little more for how many hydroxides. So here, barium hydroxide, is this a strong base? Yeah. Metal hydroxide is going to be a strong base. So let's think about what happens when that combines with water. So we've got H2O. I don't like doing it this way. I'm going to do it this other way. This ionizes, dissociates completely. So it forms a barium ion. And how many hydroxide ions? 2. So for every one of these, we get 2 hydroxide ions. So if we're looking at the hydroxide ion concentration of this strong base, it's going to be twice that of the barium hydroxide. You okay with that, or do you want me to prove it to you? I'll prove it to you. So 0.055, this means moles of barium hydroxide per liter of solution. I want to know how many moles of hydroxide per liter of solution. So how many moles of OH minus per mole of barium hydroxide? 2. I look at this, I can look at the formula and see the 2, or I can think about what happens, but I'll get 2 moles of hydroxide for every 1 mole of barium. So the concentration then is 0.11 moles of hydroxide per liter. Or we say the concentration of hydroxide ions equals 0.11 capital M. Any questions? What about this one? 1.05 molar C5H5N. Is that a strong base? No. Metal hydroxides are strong bases. That's not a metal hydroxide. It's a weak base. If it wasn't in a problem like this, I wouldn't even expect you to recognize that as a base. But we definitely know it's not a strong base. So then what's the hydroxide ion concentration? Is it equal to 1.05? It's less than 1.5 molar. Because when this ionizes, it only ionizes a little bit. So the hydroxide ion concentration is going to be less than the concentration of the base itself. What about 0.45 molar sodium hydroxide? Strong base, weak base? Strong base. It's a metal hydroxide. How many hydroxides per mole of sodium hydroxide? 1. So we don't have to multiply or anything. It's just going to be the same, 0.45 molar. Questions?